Sorry, everybody. I wasn't recording the beginning of that. Um, my bad. What you'll have to do if you want to catch up on this earlier stuff is just go watch the other classes video. They're all posted in the same place on YouTube, and catch up to this point, and then you can jump back in. Sorry about that. I've got a million different things on my mind, maybe an infinite number of things on my mind, and I did you wrong, man. I did you wrong. You're all saying it's okay, but you're not the ones who missed the class. It's okay. I guess you're the most important ones anyways. You're here live in the moment. It's always more interesting that way. Okay, let's keep going. C. I'll draw this for you. I have a reference. It looks kind of like this. Okay, this is a piecewise function. Yeah, it's no problem. I just forgot to hit the record button. It was my bad. I made a mistake. What kind of discontinuity is this? Is it going to infinity at an asymptote? Is it jumping or is it removable? Yeah, you got it. Most of you are saying this. This is a jump. Why is it a jump? It's because you would have to jump from one value to another. It's not going to infinity, at least not quickly. There's no asymptote. It's just a jump. So I'll just call it a jump and leave it at that. It's a jump discontinuity. Which value of x are we not allowed to have? Okay, I see your question there, Ibrahim. I'll cover it in a second. Which value of x does this function not have? Well, let's look at this. All of these x values are okay. You know, on the left side, that function is continuous there. On the right side, the function is continuous. We can draw it without lifting our pencil. The problem is at x equals 0. So I'll say here, we're not allowed to have x equals 0. It's not possible. That's because, look at this. X can either be less than 0 or greater than 0. It can't be equal to 0. So the x value cannot be 0. It's not in the domain. So Ibrahim, which part of the question do you not understand? Do you mean the type like any of the graphing questions? Or do you mean this particular piecewise question? This question, okay. So let me just try to make it as clear as I can, okay? Follow me here. The function, it's in two pieces. When x is less than 0, it looks like x cubed. So when x is less than 0, it's going to be this function, okay? That's the left side of the function. When x is greater than 0, which means on the right side of 0, the function looks like this. It's a totally different function, but it's all right. On the left side, it's like one side, and on the right side, it's another type, and together they make the function. The problem is, if we look carefully at our conditions, it said x can be less than 0. It said x can be greater than 0. There's no x equals 0. It doesn't say what x is when it's, sorry, what the function is when x is 0. So it's not in the domain. There's a missing piece. There's a missing x value for the domain. So we say that it's not in the domain. There's no possible x value at x equals 0 because it's not been defined. Does that make sense to you? Okay. So I got to keep going. I don't want to leave any downtime here. Just jump out at me. Tell me when you need me to answer a question. Otherwise, I'm going to keep going because there's lots to cover. None of it's super hard, by the way. It's actually quite easy once you do enough practice, but the introduction is the hardest part. So I'll do my best to help you out. Graphical limits. Graphical limits, or graphically, first of all, what a limit is it's asking what is the y value as we get closer and closer to an x value. So what the heck does that mean? Okay, well, let's read the definition. The limit is the value of the function we expect as x approaches some value. So in this graph it says we can approach x equals 3 from the left or right. Okay, let me try to break this down. Just look at this. This is when x equals 3, okay? when x equals 3, it means we have to look at the function on the left side of it and on the right side of it and see which value it's trying to get to. What a limit means is we're allowed to get close to x equals 3. We're not allowed to touch it. And we need to kind of like tell a story about what's going on. Let me try to make it clear for you. Let's just say, look, when x equals 3, we can pretty much tell that it's going to be 2, right? In this case, we can tell it's 2. You know, down this line, we can see it's 2. But there's two ways we need to look at limits. We need to say, what's the value from the right side and from the left? Sorry, did you have a question for me? Okay. All right. Just follow me here. I'm going to try to make this clear to you. Look at this function. As we get closer to x equals 3, the x value of 3, what value is it trying to get to? It might seem like a silly question, but it is important for later. You know, if you imagine the rest of this function being deleted, you know, just pretend you didn't know what was over there. It's clearly trying to get to what value? It's trying to get to the value of 2. Trying to get to 2. We can see that the y value it's trying to get to 2. It's not, we're not talking about the x value. We're saying as our function creeps over more and more to 2, I see that, yeah, it'll become 3, okay? So in math terms, what we call this, it says the limit as x approaches 3 from the right. Let me be very clear here. This little tiny positive means from the right. The way we write this down is as follows. We say the limit as x approaches 3 from the right, that's that tiny little plus. The limit as we get close to 3 from the right of the function. What y value is it trying to get to? It's trying to get to 2. All right, that's our right-hand limit, our limit on the right-hand side. Okay, it's as if, let me see if I can make a good point here. Not how I expected that. Let's do the same thing from the left side. What's the limit as we come from the left? This probably shouldn't be too much of a surprise what's going to happen right now. But let's zoom in. We get closer and closer. Pretend you don't know what happens on the right side. What value is it trying to get to? It's trying to get to the same y value. Which y value is it trying to get to? It's trying to get to 2. So the limit as x approaches 3 from the left side of this function is 2. Now this might seem silly, but it is very important for what's coming up later, okay? Both of these things together, if these are both true, they're both equal, it means the limit of the function, or in other words, the y value that we approach when we're trying to get close to this x value is 2. In other words, we say the limit exists. So this is a weird concept. It's kind of difficult to explain it in the beginning or make sense of it, how would it affect our everyday life. But for math, there's some really important extensions that it comes to. So Muhammad al-Naki said, so both of the limit will have the same answer. In this case, yes. So let me just recap. If you're someone, oops, let's just say you're just a little person standing on this side of the function and saying, hey, what does it look like when we get to x equals 3? And you're like, hey, I can see that it looks like a 2. And then the person on the right side is like, well, I think it also looks like a 2, and you agree that it has a limit. But many functions don't have limits. Let me just show you what I mean. So Muhammad, maybe you had a function that looks like this. Okay, maybe you had a function that was crazy looking like that. Well, someone on the left side, you know, maybe it's at this point, they would say, well, I think the function goes to 5. And the person on the other side might say, hey, you're crazy. I think the function goes to 2. And in that case, the function would not have a limit. The limit means the function that the value it's trying to get to. You see what I'm saying? It's almost like we're playing a game. We're not allowed to have the x value that we're talking about. We're just allowed to get close to it. And you have to describe what happens as it gets close to it. And it has a really important consequence for calculus later. It's actually, calculus is built off of this idea. So for this graph, it's very simple to see what the limit's going to be. It's going to be 2. Numerically, which means using numbers, if we were given this graph, we can actually say what the limit's going to be. It says from the left side, let's just say we wanted to approach 3 from the left. So we're considering the limit from the left. Let me draw you a little number line to help you understand this. Let's just say we had the number 3, okay? We're not allowed to get to 3. We're only allowed to get close to 3. So what's the function value when we're at, say, 2.9? On the left side, what's a number really close to 3? It's 2.9. If we put that number into this function, it gives us back 1.997. You can actually type this into your calculator. Put in the x here. Put in 2.9, something close to 3 but not quite 3. It'll give back the number 1.997. If we put in a number even closer to 3, so maybe we put in 2.99, which for many students, that's like, if you had 299 real, you basically have 300 real, right? Isn't that close? If you put that number in, this is the number it gives back. And we keep playing this game, get closer and closer to 3, it gets closer and closer to 2. So the limit is essentially 2. And now I know this is probably over your head to some extent, but this is the idea we're going with here. Let's consider what happens from the right. What's the limit from the right? So we have to stand on the right side. We always get closer to the number, but we actually never get equal to the number. We just, for example, look at this. When we play the same game here, we put in numbers that are closer and closer to 3, but from the right side. You know, we get super close. We get as close as we possibly can, 0.0000001. If you put that number in, you're going to get a number super close to 2. But it'll never be exactly 2 because we're not allowed to put the number 3 in. It's just so close that everyone knows what you're going to get. It's called the limit. Now again, it's not infinite because look, this number is almost 2. 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 For all real practical purposes, we can say that the limit is going to be 2. As we get closer and closer to 3, x equals 3, the limit will be closer and closer to that specific value. In other words, it says to approach a value means to get close but never equal to the number. I'm not going to lie. This concept is like, it's hard to understand. It just is. But the concept is, it's a simple concept, but it's probably something you've never ever had to think about. So once again, the idea is you choose a number, for example, x equals 3, and you're like, what happens as we get super close, infinitely close to that value from the right and from the left? Does it have a number? Does it go to infinity? Does it go down? What happens? Just describe that number to me. And by understanding that, we can do more things with it later. Okay? Just for now, just take it, just trust me. I want to make one more note here, and this is very important. For a limit to exist, the left hand and the right hand limit must be equal. So like we had earlier, the limit on the left, as long as we're speaking the same language, person on the left agrees with person on the right, we have a limit. If they don't agree, we don't have a limit, and that's okay. So let's actually try to do some examples. Even if there were a jump, well, that's a very good question. I'm going to show you. It'll become very clear with the examples. I promise you it's going to become clear. So let's go straight to it. These are graphical limits. says determine the right-hand limits, left and right-hand limits as x approaches 0 for the following graphs, and determine if the limit exists. So first of all, I look at this graph, I can see that this is continuous. There's nothing crazy going on. It's a well-behaved function, okay? It says, what's the limit as x approaches 0 from the left? So let me make this clear. We're trying to get to this value. So really we need to say, what's going on with the y values? Let me look at it from the left. From the left, we're saying, all right, someone on the left side, imagine the right side is in the dark. You know, you're not allowed to see this function. It's hidden behind a door. On the left side, you're like, well, clearly it goes to 1. Clearly it goes to 1. So you would say, oops, I keep doing that, sorry. The limit of the function as x approaches 0 from the left, that's my little negative sign, of whatever this function is, we can say the left-hand limit is 1. And make a note, this is a minus. Let's do the same game for the right side. Standing on the right side, which value is it trying to get to? Clearly, the same 1. It's saying that the limit as x approaches 0 from the right side, and that's very important that we see that that's a plus now. It means from the right, equals 1. If the left people and the right people agree, which never happens in the United States, but left-hand people, right-hand people agree, then the limit exists. So we're going to say the limit exists. There is a limit. There's a number that the left hand and right hand can both agree on. So we just write out, we don't have a plus or minus. Notice I didn't put a plus or minus on that 0. I just wrote it directly. The limit as x approaches 0 of the function is 1. Let's do another example where the limit doesn't exist. This will answer Abdo's question, hopefully. So in this second question, we can see what type is it? Well, it's a jump. Hopefully you can see it's a jump. When x is 0, what are the values? What's the limit from the left? Well, again, think about one side is in the dark. Let's hang out on the left side. The limit as x approaches 0 from the left side of this function is actually 3, which I just see at Mohammed, you got that answer. That's because on the left side, you would swear, you could swear, anyone who is asking you, of course, it's going to 3. It's going to 3, of course it is. How could you say anything different? But if you're on the right side of this function, you have a totally different perspective. You're telling, you can say without any shadow of a doubt that the limit is going to be 1. And you're both right, but you're on different sides of the function. And if you don't agree, it means it doesn't have a limit. So these numbers, they're not the same, obviously. You can see that much, I'm sure. So we can say the limit does not exist. There is no limit for this function. There is no value in the center there that we can agree on. So the final answer here, I usually write it as DNE. The reason I do that, DNE does not exist. It's just shorthand, it's easier to write. All right, it's a shortcut. Just like these were the same. If they're the same, the limit exists. If they're not the same, the limit doesn't exist. Sah? It's okay? That's all we're going for. Simple concept, just a very new concept, I'm sure. Let's do 2 more. This one, if you look very closely at that point there, it has a hole. The thing about functions that have a hole in it is that even though they're not continuous, they still have limits. So I'll show you why. It should be clear, actually. The left side and the right side can both agree that they're going to the same place. Even though there's no function value there, even though we would have to divide by 0 to get a number, limits let us know what the number would be. And that's very powerful. Actually, limits, one of the most important things about limits is it lets us divide by 0. Calculators can't divide by 0. You can't just type in divide by 0 on a calculator and get it to work. But with limits, we're allowed to figure out what the value would be. And that's hugely important for some of the stuff that we do later. So we're now learning how to divide by 0. So from the left, the function value is 1. From the right, you'll get really good at writing these down. From the right side, the function value is also 1. Even though that doesn't exist, the number 1 doesn't exist there actually, the limit does exist. So the limit as x approaches 0 of the function is 1. Oops. Even though we're not allowed to put it in the function. Even though that number doesn't actually exist, we're allowed to give the limit, okay? So this is one of the reasons why limits are helpful. Let's do the last one. What type is it? What's the last type? Anyone ready to go? It's infinite. Yeah. From the left, what do we got going on here? From the left side, someone's going to yell at me and say it's negative infinity. Someone's going to yell at me and say it's positive infinity. They clearly can't agree, so the limit doesn't exist. Let me just quickly write out the full answer. So on the left side, someone would definitely say it's negative infinity. The right side, they say positive infinity. It goes down forever or up forever, depending on the side you're talking about. So they say the limit doesn't exist. So Mohammed, you got that. All of those answers are perfectly fine. So as long as you say the right idea, I don't care how you say it. So for example, Abdo, you said doesn't exist. Ali, you said non-existence. Mohammed, infinite. They are all saying the basic things. Just be sure that when you actually give the final limit, it either exists and it's one limit, or it doesn't exist. The only way to check it is to check the two sides. All right? All good. We're going to move on. Got lots to do. I'm going to talk a lot today, but I'm trying to make sure you get as much in as possible. Careful, careful. So Ibrahim, when the limits are infinity, so let me be very clear. If one limit is negative infinity and one limit is positive infinity, those are not the same, so you don't have a limit. But there are plenty of cases where they're both infinity. And in that case, it does exist. The limit is actually infinity, okay? You're allowed to have a limit of infinity. It's not a problem. Because they both go up together. All right, so we just covered graphical limits, but most times that we do limits, we don't actually know what the graph looks like. So we have to figure out what the limit is, what that number would be for the y, without a picture. And honestly, for limits, it's pretty easy. It's one of the easier topics in the course once you do the practice. So let's just work through this. I'll try to help you out. It says the graphs below are all continuous. And I'm going to skip over this stuff. I'm not going to fill it in. For continuous graphs, for any value of x, the limit exists. Okay, so any continuous function, if you substitute the value indirectly, so maybe, let me show you actually, I'll be clear. You can put in any x value, so let's just say 2. So over here, 2. Put in 2 into this, put 2 minus 1, square it all, take away 1, it's 0. For the next one, let's just say, put in negative 1. You just directly substitute it. If you put negative 1 into this, you get a 0. You can check it yourself. What about this one? Let's put in 0. When x is 0 here, what's the limit going to be? Let's just say that the function looks like this at this point, or we can put it in. It gives us the value 5. Okay? Let me check that actually. 0, no, it's 1. Not bad. But the whole point is, if there's no crazy jumps, we just directly substitute whatever the limit number is. We're good. No, the continuous aren't all equal to 0. You just directly substitute. Let me just show you. Whatever this value is here, you just put it in for x. And it'll give you a number, that's your limit. Finished. Or if you had -1, you just put it in for x. Put it in directly, that's your limit. Is it -2? -1 cubed, that's -1, minus -1 is 0. I think maybe you didn't use brackets. Is that okay? Just be careful. Anytime you substitute your number in, especially with negatives, try to put brackets around your x values, because otherwise your calculator might give you something that's not actually right. Let's keep going. So for graphs that are discontinuous, we just need to make sure that we use points that belong to the domain. I'm not going to get too much into it. I'm just going to say, if you do that, the limit will exist. I want to show you what this means by doing examples. I don't like to talk through the theory too much. You're just going to get lost, okay? What I do want to show you, and this is probably the most important thing in the whole unit, and I mean that literally, this concept is the most important thing for limits. What it's trying to say is the direct substitution rule. It means for any limit, for any function, if we have nice continuous functions, we can just substitute the value in, and the limit will be whatever that substituted x value is. So what I mean is, you just take the value we're talking about, x approaches 2, x approaches 3, take that number, put it in for x, get the limit. That's the first thing you should always do. If that doesn't work, we'll try other ways. Okay, let me make a little note here. It says that if A is in the domain, we can just substitute the value. What limits are okay? As answers for limits, what limits are okay? Well, we can say limits of infinity and negative infinity are okay. This is just a reference for later. Limits of 1 over 0 is actually even okay. That's might be weird to you, but limits let us divide by 0. The problem is, the only issues, limits of 0 over 0 or infinity over infinity are not okay. So just make a note of that, take a picture of it or write it all down. That's an important note that we need to refer to later. And when it comes up, I'll tell you. Right now, I'm just throwing information at you. It's probably not going to stick yet. But once we do the examples, it will start to make more sense. And I think you'll agree that it's not that hard. I'm even going to give you a flow chart that says, if given this, do that, that, or this. If you're given this, do this, this, or this. So eventually, you're going to have a very clear picture. All right? For now, just trust me. I'm taking you on a journey. You don't know where you're going yet, but just enjoy the ride, okay? Just enjoy the ride. Let's do some examples. It says, determine the following limits using direct substitution, if possible. Sometimes it's possible, sometimes it's not possible. Let's go ahead and see. So first of all, take this 4. All it means for direct, it means literally substitute it directly. So just put it in. 4 squared minus 7. What's 4 squared minus 7? 4 squared is 16. 16 minus 7 gives 9. So the limit is 9. Doesn't matter how complicated that function is, doesn't even matter what it looks like. All we know is that if we're going close to the x value of 4, at some point it's agreeing that the y value is 9. Halas, easy peasy. Let's do the next one. Take that 2, put it in for every x that you see. So I'm going to say 2 squared minus 3, 2, 2. So let me just make sure you know I'm substituting. Multiply that out. I think you get a 4. I'm actually going to move it down here. This gives 4. So the final answer is 4. That's our limit. That's all. Moving on. Let's do the next one. This is e to the power of 0. E is just a constant like any other number. 0 is not special either. And then we take 0 and square it. Anything to the power of 0 is 1. 0 squared is still going to be 0. So it's 1. Let me be clear on this. Anything to the power of 0 is 1. You can put it in your calculator. Put 1,000,000 to the power of 0, it'll still give you 1. Okay, so this limit is 1. Finally, can we substitute this? I think we can. Take 5, put it in there. That's 5 squared minus 9, which is 25 minus 9, which is 16, is 4. So the limit here is 4. So direct substitution, really quick and snappy. It doesn't always work. In fact, most of the time, it doesn't work. But when it works, it's great. Okay, it's the fastest way to do this. There are many cases where it doesn't work, and I'm going to teach you how to handle that. But always do that first. Okay, step 1, try to directly substitute. Let's take a look at these examples. Let me know if you need to go back. We only directly substitute. You might notice that we could probably cancel some factors here. That's true. For now, we're going to ignore it. We don't need to cancel it. We're just going to do it if possible. Let's do a few of them. The first one, what do we have? We have to put in 0. So 0 outside of 0 minus 2. 0 minus 2. So this is 0, yeah? What's that going to give us? Why won't it turn blue? What does it give us? 0? Some students say it gives an error or it's undefined, but it's not. 0 divided by something is still 0. It's the opposite we need to worry about when we divide by 0. So the limit's 0. As we approach both sides, it's just 0. Let's move on to the next one, see what happens. The next one's the same case, actually. I'm going to do C instead. So let's look at C. Let's put in 2. So this is 2 squared minus 4. 2 minus 2. What do we have now? This is 0. This is 0. This is a problem. I think, Ali, are you saying that it's 0, it's 1 because 0 divided by 0 must be 1 because it's the same thing on top and bottom? It's a weird one, isn't it? I mean, if you put that in the calculator, 0 divided by 0, this Casio says math error. You know why? It's because calculators can't divide by 0. No matter how clever they are, they can't divide by 0. So we're forced to say that the limit does not exist. In fact, the limit might exist, but we can't do it. Okay, so remember there's 2 cases where we have problems. 0 divided by 0 or infinity divided by infinity. And there are tools to solve that. We can do them. But for now, we're going to leave it. I'm just going to say we can't evaluate using direct substitution. That's all I can really say. I am going to say we need other methods. And I'm going to say we're going to do those very soon. There's other very simple ways to evaluate this. For now, we don't know. We just can't say what the limit is. All right? 0 divided by 0. It's like if you had 0 pizzas and you want to cut it into 0 pieces. Well, first of all, what does it mean to have 0 pieces when you don't even have anything in the first place? It just doesn't make sense. Like, you can have no pizza and cut it into 4 pieces. You still have no pizza. The problem is when we have 4 pieces, 4 pizzas, and you want to cut it into 0 pieces. You have 4 pizzas and you want 0 pieces. Wouldn't you have to delete the pizza? We're not allowed to delete the pizza. Anyway, don't divide by 0, folks. Dangerous. Let's do one more, and then we'll move on. I want to teach you the next method. Let's do, I'll do F. I'll do D and F, actually. E you can do yourself. They're not complicated. D, directly, 1 over -1. Oh, that was super simple. It's just -1. So the limit is -1. Even though it looks crazy, it's actually got a limit. F, well, let's try to do it directly. 1 over square root of 5 minus 9. That's 1 over the square root of -4, huh? So in this case, we have to say it doesn't exist. Because limits are something we can only do on real numbers. We're not dealing with any imaginary numbers right now. So we just say it can't be evaluated with direct substitution. Maybe it could be evaluated some other way, but as far as we're concerned, we're going to say that this does not exist. At least not using direct substitution. Okay? I'm going to quickly do the extension here, down here. First of all, are there any questions on that? Or are we sort of okay for now? Again, for F, you don't use imaginary numbers. If it can't be done in real numbers, then it doesn't exist. What values are not in the domain for the above functions? For A, what values are we not allowed to put into this? Well, look at the bottom, x minus 2. So we're not allowed to put in x equals 2. So x can't be 2, not allowed. For B, what value are we not allowed? X is not allowed to be -2. We'd end up dividing by 0. C, let's see, it can't be 2. Again, it's not allowed to be 2. D, x is not allowed to be 0 because in D, we have the x on bottom. We can't put x equals 0 because we divide by 0. For E and F, that's more of a challenge question. They need to be greater than 4, greater than 9. But I'm not even going to write them down because I don't want you to worry about those. So just forget about those for now. I want to focus on the meat. We're nearing the end of the course. I don't want to bog you down with something complicated, okay? So just E and F. If you're curious, you can look up the answers, but for now, we're going to skip them. Some of these notes here are done in a weird way. They're done in a weird order. I'm just going to skip a little bit of this, but let me try to help you understand this section here. It says, when A is not in the domain, or in other words, when we have a case where we're dividing by 0. So a case where we would divide by 0, we can sometimes fix it using algebra. That shouldn't be a surprise because I told you way back in the beginning of the class that we're allowed to cancel things that would make wholes, okay? Look at this function, x minus 2, x minus 2. Now, if we just cancel that directly, let's try the limit of the new function. What's the new function? The new function is just x. Can we put 2 into that? Of course we can. And it turns out that even though we're not allowed to have that number in the domain, we can still get the limit at that point. So it's like when we looked at the graph, even though it has a hole there, we still know what it was going to be. So this is how we do it by hand. And it lets us divide by 0, which is kind of nice. Doesn't always work. Usually does. So I'm going to make a note. When it says try algebra, it usually means factor. And by factoring, I mean try to find things on top and bottom that can cancel each other. That will let you get the limit. All right? So whenever you can't do it directly, do it using factoring. You can skip this. This is a case where I don't like how the book did it. Just skip this. Skip it. You're welcome. There's a little bit of a note here. It says that sometimes we can't fix it using algebra, but you can look at it and notice that it has an asymptote. So look at the graph here. We notice that the function x equals 0 of x squared, if it looks like this, what's the limit going to be? Well, this is like Mohammed asked me earlier. As x goes to 0, both sides are agreeing. That side's going to positive infinity. That side's going to positive infinity. So the answer is positive infinity. For this case, as x goes to 0, we have a problem. From the left side, it goes to negative infinity. From the right side, it goes to positive infinity. And so the limit does not exist because the left-hand side can't agree with the right-hand side. So I don't know why they put those graphs here. It's not really the right time to talk about that, but I guess you had to put it somewhere. So let's just take those as a fact for now and move on. We'll come back to that idea a little later in tomorrow's class. Okay, let's actually do the simplifying. This is stuff that I think you'll find quite simple once we get to it. Find the following limits by simplifying algebraically if possible. First things first. What was the first thing I said to do? No matter what, when you're given one of these questions, what's the very first thing I said to do? What's the first strategy? Do you remember? No, even before factoring, there's something I said was super important. The very first strategy, and that's direct substitution. There is no reason why you should do another type of strategy if it can be done by direct substitution. So at least take a look at it and see if it would work. So I'm just going to look at this one, A. If I put in 1, I get 1 squared minus 1 over 1 plus 1. That gives me, negative 1 squared. Negative 1 squared minus 1 over negative 1 plus 1. That gives me 0 over 0. That's why I have a problem, right? So Mohammed, you're saying it wouldn't have an answer? No, it wouldn't have an answer if we do direct substitution. So to be very specific, this question has 0 over 0 form, but we're allowed to factor. Now that direct substitution is clearly not working for us, try to do a factoring. So let's factor this sucker. So let's keep going. We're going to get the limit. We haven't substituted yet, so we need to keep writing that limit. Factor the top. Factor this piece. It's the difference of squares. Hopefully you know what that means. You have the square root of the first one. Write that down in both places. You get the square root of the second one. You write that down in both places, right? And then you put plus and minus. That's if you have two square numbers, x squared and 1. On bottom, x plus 1. So Ibrahim, you're saying the answer is negative 2. I perfectly agree with you. What we have now is that we have x plus 1 on top, x plus 1 on bottom. Now, let's substitute in. We end up getting 2 minus 1, which is, wait a second, not 2. I'm just so used to 2s. Negative 1 minus 1, which is actually negative 2. Okay, so about 10 minutes ago, we had questions that we couldn't solve because it gave us 0 over 0. Now, because we know we can factor first and it still gives us the limit, now we can figure out what the function is. we can figure out what the limit is at that point. Even without knowing what the graph looks like, we know that the y values are going towards -2. All right, so the final answer here is -2. Let's try the next one, just a little bit of algebra, okay? This one's a little tricky. I'm going to take this off to its own little space just to solve it out first. You can put those next to each other. Hopefully you know that. You can also do it in your head. If you work that out, you get this. So let me explain what I'm doing. I'm multiplying the first two numbers. I'm then multiplying 3 by h, which gives me 3h. You multiply that by 2. Or you can expand the whole thing out. And now h squared. So Zada, when you said, can we solve them now by this way? Okay, 1 second. I've got 2 questions. Zada, I want to answer yours first. Which one are you talking about? You're saying we can solve them, the limits, the old limits that we said couldn't be solved. We can solve them using factoring. I'm going to assume yes. Yes. So look, in this case, for example, we could factor the top. It would cancel the bottom. We would get a limit. The square root one, we're not quite so lucky. I'm not sure that that does have a limit. But for sure, C does, right? So yes, the short answer is we at least have another way of checking to see if it has a limit. It might still not, but at least we can check. And Mohammed, you said wait, why 2? Do you mean for the first question? For B? Okay, you meant why did I multiply the middle term by 2? So let's just look at this. If you multiply first ones and the last ones, insides the last ones, you get this. But for squared numbers, if you're squaring something, this is always the same. It's the same as just that one times 2 gives 6h. So you can just multiply the outside numbers, multiply by 2. It's just a faster way to do it. Yeah. Okay, let's continue. We haven't done the limit yet. Be very, 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 very careful that you don't get rid of that limit in front, because you haven't done the limit yet. Simplify first and then we'll do the limit. So this is 9 plus 6h plus h squared minus 9 over h. Ibrahim, you're saying not sure, but is it possible to use the conjugate? There are cases for sure that we need to use the conjugate. Not this question, but in some cases we will do that when we get square roots on the top. But that's going to come a little bit later. I don't want to throw too many things at you at the same time. All right, so let's see what we have here. 9 and 9 will cancel. That will leave us with 6h plus h squared on top. Factor it. When we're in limits, I'm giving you full permission. Factor as much as you humanly possibly can. Just always factor, 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 factor. The more you factor, the more success you're going to have, because it's just the way that these functions work out. Factor the h, exactly. 6 plus h over h. Cancel, cancel. Now we can substitute in. Now we're doing the limit. Put in h directly. You get 6 plus 0 equals 6. So the answer is 6. The limit for this function is 6, even though you technically are dividing by 0. The thing is, limits let us get the value that calculators can't. You know, if you use the graphing calculator, it's going to tell you it's undefined. But we know it actually equals 6. So, I don't know. To me, it's interesting that we can actually divide by 0 if we kind of mess with the math a little bit. Pretty powerful consequence, actually, of limits. Maybe I'm just a nerd. I don't know. It's probably both. Okay, let's try a few more. I'm going to try maybe C. because most of these feel the same once you do enough of them. Let's do C and E, actually. So if we try C directly, I think what's going to happen, if you put 3 in there, you're going to divide by 3 on bottom. I think on top and bottom it gives 0 over 0. So we're going to factor and cancel and see what happens. I can pretty much guarantee you, if you can factor something that's a limit, you'll probably be able to get the limit. It's just the way that this goes, which is why a lot of students end up finding it easy, because there's only so many rules. 3, okay, factor the top, factor the bottom. The hardest part about this is knowing how to factor. So let me remind you, you're trying to figure out two numbers that multiply to make -3 and add to make -2. So you have two choices. You either have 1 times -3 or you have -1 times 3. You need to multiply to make -3, add to make -2. We have this one. That's basic trinomial stuff. You should know how to do that. Ibrahim, yes, the answer is 4. You can go ahead and try E if you want. Once we factored this, bam, bam. Pretty nice. I'm going to do the limit now. I'm going to put 3 in for x. I have 3 plus 1. Limit is 4. So Mohammed, let me do a little aside for you to remind you how to do trinomials, because it's going to come up a lot. So I'll come back to that. Let me just look at this. I want to factor this. We know it's going to have this form. In this space, we need two numbers that multiply to make this, and add to make that. So the first thing you should do is consider, what are all your factors of 3? Well, you can only make 3 in one way. It's 1 times 3. How do you make -3 though? Well, you either have -1 times 3 or you're going to have a 1 times -3. Okay? Those are your only two possibilities. So those are your multiplications. Which combination here, this one or this one, is going to add to -2? Well, this one. Because 1 plus -3 is -2. So that's the combination you need to take. A +1 and a -3. Is that okay? Is that more clear? Yeah. So that will always work. That method will work no matter how big the numbers, as long as the factor in front of this x is 1. You know, if there's a little 1 there. If it was a 2 or a 3 or a 4, it's more complicated, but I'm actually not going to ask you those. So don't worry too much about that. All right, let's get a little bit more done. We'll do the same factoring here. You'll get a little bit of practice. So Ibrahim, you got 3 over 4 for the for E. I agree with you. That's exactly what we're going to get. If you directly substitute in this, then you're going to get 0 over 0 form. So we need to factor. The limit as x approaches 1. We're going to get 2 chances to factor. X, 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 x. On top, what two numbers multiply to make -2, but add to make 1? And if you work this out a little bit, you know, do a little bit on the side of the paper, you'll see that that's true. The order doesn't matter. On bottom, which two numbers multiply to make -3 and add to make +2? It's definitely 1 and 3, but what about the signs? Well, the sign always gets stolen from the bigger one, okay? That's a little hint. Whatever sign this is going to be the sign that we put with the bigger number. This is the number. So practice that. Get some practice on those factoring. If you want to practice it like with Khan Academy or something, it's called factoring trinomials. And there's millions of practice problems out there. Once we get that, we're done. I'm going to substitute now. We have 1 plus 2 over 1 plus 3. That gives us 3 over 4. That must be our limit. Okay, that's our limit. Okay, so far? Now that we've done these styles, I mean, I've only taught you 2 things so far. There's direct substitution, which is like, don't even think about it, just stick the x in, see what happens. And there's factoring. And those are the only 2 things we're going to need to worry about right now. There are a couple other methods, but for the most part, that's it. If you're trying to get x as it approaches a number, these are the methods that we have. And that's why I'm not going to do D, I'm not going to do F. I'm not going to do the rest. They're pretty much the same. I do want to graph it though, because I have a thing for graphing, as you know. And the more you graph, the more you understand these math concepts. So let me just graph this. Plus x minus 2, x squared plus 2x minus 3. Okay, this is our crazy looking function. What I know is that I can't, something weird is happening at 3 over 4, I think. Let me make it clear here. Our function, f of x, f at 3 over 4. Oh, sorry, I'm trying to go to 1. What am I thinking? F when the value is 1, it's undefined. Okay, this is the power of limits, I guess. When f is 1, you can see it's undefined. Sorry, 1 second. Okay, anyway, my point is, the original function, we want it when x is 1. We can't actually get the value of the function because we'd be dividing by 0. But when we do the limits, we can figure out what the function value would be. So it should be 0.35. Let's zoom in on 1. And the value there, if I look in real close, if I get as close as I can't actually touch it because it'll be undefined. But see that? 0.749, 0.75. It's 0.75, which is 3 over 4. Okay, so I'm probably overwhelming you. I know it's been a long day. I know you have an assignment. I've got to do just one more question. I'll do it quickly, and then you can relax before we start the assignment, okay? So the rest you can do for practice. These graphs, if you want to try these, use Desmos to get the graph, and then check the limit. Let me do one more type, and this will be the last thing we do today. It says, let's take a deep breath, relax. Using the table below, determine the left and right-hand limits of the piecewise function. So this is a piecewise function. We know that because it has a left side and it has a right side. So as x goes closer and closer to 0. So the idea here is that our function, if we take, for example, the value, okay, first of all, this is our left, yeah? So the point 0, what is a very, very close number to 0 that isn't 0? Well, on the left-hand side, we can say, well, 0.1 is really close. Or you might say, how about we get 10 times closer, you know? 0.1 is close, but, or sorry, negative 0.1. Negative 0.01 is even better. Or get even closer. What about negative 0.001? Get as close as you possibly can, and that's what we're doing. We're saying, try taking this x value, put it into this function, you'll get back this. something close to 1 but not quite 1. If I keep filling this out, if I take this number, close to 0 but not 0, you end up getting this. If you keep doing it, you'd have to calculate this. These are the numbers that you get back. What number is this trying to get to? You know, if we were to put in, like in your calculator, put negative 0.000000001 and add 1. What number is that? It's 1. So the limit from the left is actually 1. That's what I'm trying to get at. If we do the exact same thing, consider from the right-hand side, on the right side. Think about 0. What's a number bigger than 0? 0.1. What's a number even closer to 0? 0.001. What's a number even closer? You get the idea? Try all these numbers. What you get is you get a number closer and closer and closer to actually not 1, but negative 1. So that's essentially, the closer we get, we're getting closer and closer to negative 1. That means that the limit does not exist because it's not agreeing. And if we look at the graph, it's obvious. We can see that 0 from the left says it's 1, 0 from the right says it's negative 1. So in conclusion, the last thing I'll write, the limit as x approaches 0 of this function does not exist. Okay? That's a tricky one, but that's been asked on assignments before. So just be careful that you understand what's going on. Basically, the idea is you're getting closer and closer to that number, putting that number back into the function, and seeing what we get. We're just taking these numbers, putting them in here, and then getting back our number, see what we get. Okay, so my finger hurts. I've been writing for about 4 hours straight, actually more like 6 hours straight. So I'm ready to take a break. How are you? How are you doing? You want to take a little break and then do your assignment at 5? All right. I wanted to get more covered today, but it's not going to happen. I'm just too tired. So good luck with your assignment. It opens at 5 o'clock. You have 45 minutes to do it. So the Dropbox closes after 45 minutes. Make sure you get it in on time, okay? Now I have only this section 3 and 6, but of course I'm doing prep. I prepare and do things before. You know, I make your assignments, I make your assignment keys, I make everything, right? So sometimes it takes some work. All right, I'm going to stop the recording. If you have any questions, let me know, okay? Bye-bye, everybody.